Anyway, thanks for the introduction, Rob. So for those that don't know me, as Rob said, I'm the CISO at Carillion Clinic, and not only am I into security, but I'm also into technology. So I think of myself as a technologist as much as a cybersecurity professional. And I found this topic one that kind of crosses into both of those domains. And I'm hoping I don't completely bore you to death with this topic. I'm going to go over quantum computing, what it is, and then how it will impact our use of encryption, especially the internet, the protocols that we use to secure the internet, like RSA. Is it a threat? There's a lot of hype out there. So I'm hoping to give a very simple and straightforward explanation of quantum computing in a very non-technical presentation that anyone here who is quantum savvy might say, I have exceptions with how you're portraying things, but I think I will at least get the broad concepts across so that we can then take it to how quantum computing will impact encryption in today and going forward. All right. And there's a couple polls, so try to stay lively. At least I'll know if you're awake if you answer the questions. All right. All right, so standard disclaimer, everything that I'm presenting here is my opinion, and it has nothing to do with any position strategy or opinions of Carillion Clinic. All right. So here's what I'm going to cover. I'm going to talk about classical computing. That's the computers that we all have on our desktops, and then compare that to this new paradigm of quantum computing. Then I'm going to discuss the current state of quantum computing, and then put in my value add, my assessment of where quantum computing is currently going and how it's impacting encryption. And then finally, some next steps for the cyber security professional that wants to stay ahead of the quantum computing threat to encryption. What I'm not going to cover is these four topics. These are, these are things that also involve quantum mechanics and quantum computing. They're quantum encryption. This is a special type of encryption that leverages some of the concepts of quantum computing or quantum mechanics. Also, quantum internet is what the internet might look like if we moved away from traditional encryption and started using quantum encryption. Quantum metrology, which despite that sounding like a weather term is not, it's actually talking about measuring things down at the quantum level, down at the very microscopic, beyond microscopic level. And finally, quantum simulations. We are still trying to understand the quantum world, and quantum computing can help us by doing simulations of how quantum mechanics works. So I think we'll stay away from those just for brevity and staying focused to cybersecurity. All right, so here's a Dilbert comic for any of you that are quantum savvy. If you find yourself laughing at this, then we're not going to get into this level of detail. But if you get it, then I hope you enjoy the humor, but can sit on the sidelines as I go over my attempt to explain quantum computing at a very high level. All right. Bear with. Here we go. All right, so this is probably a review for most of you, but it lays the foundation for being able to contrast our current computing or classical computing with quantum computing. As most of you know, all the computers that we use are working on basically just ones and zeros, either on or off. That is, and how these bits, as they're called, these states, these bits that can either be a 1 or a 0, as they flow through the computer, which really is doing extraordinarily simple operations, things like OR, AND, NOR, simple comparison operations. But when stacked together, these gates, these logic gates, where it says, if it's 1 and 1, then return a 1. Or if it's 1 or 0, return a 1. But if it's 2 zeros, this is the logic that builds all of the computers today. And the example, the computer that I'm using to share this presentation with you right now has 400 million gates within it that are helping to run the programs that we run. But again, it all is just simply ones and zeros, just running at incredible speeds. And that's really but what has been the advancement of computers is making more bits run faster throughout the computer. So, but it at its core, at its essence, it's just these simple comparisons of ors, ands, nors, and nots. So that is our classical computing. I hope that makes sense. So now let me move to what is quantum. Let's contrast it with quantum computers. So quantum computers don't use bits, they use qubits. Very similar in some ways, but radically different in others. So let me explain the qubit. Qubits, like a bit, can be 1 or 0, but they also have a very amazing property that they can be in states between 1 and 0. So not wholly 1 or wholly 0. So that might take a second to process. What do you mean? How can it be in between? And the best analogy I could come up with is I want you to think of a snow globe, okay? And imagine that you filled the snow globe halfway with oil and you filled the other half with water. So here you have this quantum bit that is 1 and 0. And now imagine that you take that snow globe and you shake it. You have the oil and the water interacting, still a 1 and a 0, but now they're mixed with each other. And I'm greatly simplifying the quantum mechanics that are going on with these bits, which is where spin and other properties that define a qubit. But it's simply, if you think of that snow globe analogy of it can be 1 or 0 or a mixture of both. So this is a constantly flowing state of value, and that's called the qubit. Now, they call this concept where it can be in various states between 1 and 0. This is called a superposition. And superpositions are what distinguish a qubit from a bit. All right. Hopefully that makes sense. That's one you got to kind of take in. There's two big concepts, and this is one of the two. The second concept to grok is this really crazy property of quantum mechanics, and that is that if you have multiple qubits, and you start changing, thinking about multiple snow globes, if you start changing one snow globe, it affects the others. It affects other qubits. So qubits, changing the properties and the states of one qubit can affect the other qubits. And they're all linked together in this very predictable fashion called entanglement. So they are all entangled. Now, I know you're saying to yourself, this sounds like chaos. How can you possibly understand these things? But the good news is physicists, mathematicians have mapped this out so they understand these relationships, that as you put a spin or as you shake that snow globe or turn it, how it will affect the other qubits. And this happens instantly. This doesn't require making changes. You're not actually going and making these changes to the other qubits. You change one, the others change. You change another one, the others change. So there is this relationship that all these qubits have that are in one quantum computer. They share this amazing property called entanglement. And what that means is when you think about what our computers have to do, when we go back to those 1s and 0s and having to take each bit and put it through a logic gate and say, okay, now we're comparing it to this other one. And are they the same? Yes, no. Go through a logic gate. This is make a state change all of the qubits. So super powerful stuff, but completely predictable when done right. There is some unpredictability if things aren't done correctly, but the models of how this works are fully understood. Okay. So I wanted to do a quick comparison here. We talked about earlier the gates or these logic gates of how bits coming in, like the and, two ands, 1 and 1 will bring out a 1. 1 and 0 will bring out a 0. These are the simple logic gates or the classical gates for bits in our traditional or classical computers. over on the right, or what I see as the right, uh, are what IBM has come up with as their version of quantum logic gates. And I'm not going to begin to describe what each of these gates do, but they affect that spin. They affect that shaking of the snow globe. So you see, you have many other new ways to affect a qubit than the simple ways that we can affect bits, right? So by changing spin, by changing polarity, this allows for massive scale of manipulation of quantum bits. I hope that makes sense. We'll have questions and answers at the end, and I'll be the first to tell you I am not a quantum physicist, but I hope these concepts, these principles of when we contrast, how you can see the difference between what a classical computer and a quantum computer is capable of. So bear with me while we try to do a poll. So the poll question is, given what we've discussed, do you think that someone could write a quantum computing machine that would run as an emulator or a model on a classical computer? Let me see if I did that right. So it's a yes or no question. Let me see, launch the poll. Here we go. All right. So if I could get you to click whether you think it's possible to model a quantum computer with qubits on a classical computer that just uses regular bits.
Can I ask a clarifying question?
Yes, please.
Does it have to fully emulate the quantum computer?
Good question. I would say almost, because if you're saying are the actual quantum property, are the quantum mechanics actually occurring? No, but this is emulating what would be an expected result if such a thing were to occur. Gotcha. So yeah.
Thank you.
It would be enough that could you be able to write quantum code with those operators that we saw earlier, those logic gates? Could that be done? All right. I'm thinking I haven't seen any answers lately, so we'll take that as the answer. I don't know about you guys. That's a little small for me, so I'm gonna. What do we have here? We have 73% say yes and 27% say no. Oh. All right, there we go. All right. I'm going to close that. All right, good. So the answer is you can. In fact, the quantum, and I bring this up to make it clear that quantum computers are not doing anything magical. They're doing some amazing stuff, but it can be emulated. In fact, there is a program called QX that you can download, open source. And if you've got a powerful enough computer, it will let you emulate a 26 qubit quantum computer on your computer. So you can go in there and write some of these, you can mess with those logic statements and try to write your own quantum computing on a standard computer. All right. So now that we know what quantum computing is and what it's capable, or what it can do, or at least how it works, let's talk about the current state. So where are we today? Well, if I didn't make it clear, the more qubits that a quantum computer has, the more powerful it is. Because of that capability where changing one value can change all the other qubit values, there's power in the number of qubits. That's the equivalent of, like, with standard computers, clock speed and addressing space. That qubits are your engine for doing computation. Google made the claim of something called quantum supremacy in 2019 using a quantum computer with 53 qubits. Now, let me define what quantum supremacy is. For the longest time, a lot of these quantum computer ideas have been theoretical, and no one was ever actually able to come up with a use case where a quantum computer could do something better than a classical or traditional computer. Yes, it's a whole new paradigm on how computers work with these qubits, but what's the value proposition? And so someone had come up with this concept of quantum supremacy. Well, in 2019, Google came out and said, we've written something in a quantum computer that allowed us to generate hundreds of thousands of random numbers. And the way using quantum code, we were able to do this in, I want to say 22 seconds, in just a few seconds. And if you were to try to do the equivalent work with a regular computer, it would take 10,000 years. And then IBM, who's kind of in a race with Google on this, they said, well, that's kind of like a super weak use case, just being able to create random numbers. And we think that we could write something with a regular computer to do the same thing in a couple days. So 22 seconds is still a lot shorter than a couple days. But again, the use case of saying that this met the quantum supremacy of having a program that runs faster in quantum than traditional is still up for dispute. So a lot of people are saying we still haven't achieved quantum supremacy because the examples that have been put forward so far don't really rise to the level of being truly a quantum supremacy, where it's superior to run it in quantum. Quantum computers are actually available now from IBM and others in the cloud. With again, you saw that codified programming language. So if you had the resources, you can actually tap into IBM's cloud-based quantum computer. And there are a number of competing designs for these quantum computers. So some of them use lasers for these qubits. It's a laser, it's a beam of light. Others are using microwaves, and others are using magnetic or using supermagnets to control atoms and putting spins on certain atoms. So there's different approaches to how to make quantum an actual quantum computer. And perhaps most disturbingly for us as security professionals, a mathematician named Peter Shor published a paper that included a quantum computer algorithm called Shor's algorithm that can be used to break RSA encryption. And for those that don't know, RSA encryption is the method of encrypting data on the internet that all financial transactions run on. Like, this is the industry, this is the internet encryption algorithm. It's a public-private key algorithm. I don't want to go into the details of it, but suffice to say that we believe very strongly that a quantum computer can crack an RSA encryption key given a sufficiently powerful quantum computer. So that was the FUD, right? So that has me trying to get you nervous that these quantum computers are able to destroy the very encryption algorithm that protects the internet and all of our financial transactions. So next poll. How many qubits do you think, now that we understand these qubits, how many do we think are required to break the RSA 2048, the industry standard RSA encryption, in 8 hours of less using the algorithm that Shor came up with? So give me a second to launch this poll. Just a moment. Relaunching the poll. No. Okay. All right. Bear with me, folks. My glasses are in need of an upgrade to the prescription, so I have to see where. Oh, I see what I'm doing. Got it. All right. So let me launch the next poll here. Here we go. All right. So how many qubits are required to break the RSA 2048 encryption algorithm in 8 hours or less using Shor's algorithm? So here are some options: 256, 1,024, 512,000, 1 million, 20 million. How many of these qubits do you think we need to get to? Keeping in mind that right now we're playing with quantum computers. That cloud-based quantum computer that IBM has built has 62, in the low 60s number of qubits. All right. I'll leave the poll open for a couple more seconds. Okay, and 3, 2, 1, and we'll end the polling. So what do I show results? There we are. Okay. So the answer is 20 million qubits are needed. 20 million. We're at 50, 60 right now. If you want to break RSA in a timely fashion, you're going to need a quantum computer that has 20 million qubits. That's so massive when you think about where we are today. It's hard to imagine. All right. Does that surprise anyone? Hopefully it does. Hopefully that puts some relief into that earlier statement about how RSA has been cracked, right? So here's where I come in and start giving you my opinion. And Rob Garby was telling me that these are going up on YouTube. So I'm hoping my predictions, which by the way are entertainment purposes only, do not hold me accountable. This is just my sense, more as a technologist than a security professional. Here's what I think. So IBM's latest quantum computer is running about 65 it has 65 qubits of power. And this picture that you see here on the right, that is the platform where they're trying to build what the size of a quantum computer that could hold up to, they hope, 1,000. So look at the size of that thing and realize that could max out at 1,000. And then consider the difference in size between 1,000 and 20 million, right? We have a long way to go. So as far as quantum being a serious threat at this time to RSA and other strong algorithms, I don't feel like we're anywhere close. I mean, it's tens of millions of qubits are potentially needed. Even if it's just in the low millions, 1,000 is a long way away from many millions. So the other thing is that these current quantum computers, as we understand them, they simply don't scale. As you can see, the size of these are massive. And the idea of being able to pack millions of them using the current technology, it just doesn't seem at all feasible. Yes, so here's what let me just flip to the next slide. So anyone who knows anything about fusion, this was pulled from some British newspapers in January of 1958. The big, as you can see, all over, a son of our own, the scientists had figured out nuclear fusion. This is the holy grail of nuclear energy. Right now, all the nuclear reactors and the bombs that we make, they're all fission, but this is fusion. This is the way the sun's nuclear works. And in 1958, they had all the formulas. They had built a fusion reactor called Zeta that for a brief moment created a fusion reaction here on Earth. It was so exciting. We're going to finally see fusion power. We don't have fusion power yet today. We're close. They're building a reactor that they're really hoping will do fusion, but right now it's still experimental. This is 1958. How many years ago was that we thought we were, everyone's so excited that this is right around the corner. And folks, not to be a contrarian, I have concerns that quantum computing, to get to the scale that we really need it to get to, may be like fusion power. There's a running joke that says fusion power is 10 years away every year. It's always 10 years away. And so it's something to keep in mind. A lot of times people will hype up some of these new technologies, but until we actually see massive breakthroughs where we're out of the thousands or even the dozens right now, we're in the dozens. When I start seeing 5,000, 10,000 qubit, 50,000 qubit, okay, they've gotten past some of these limitations. But right now, we're incrementing in small jumps. We're jumping 3 to 4 to 5. We're adding on. Doesn't mean it can't go higher, but that's where we are today. So my prediction, until I ask Rob Garby to pull this down in 5 years when I'm way off, is that uh, quantum computing isn't a threat at this time. So let me move to the next slide. And so this is another thing I wanted to touch on too. Just didn't know where to fit it in. Quantum computing does not replace classical computing. I thought this is an IBM slide that I took from their presentation on quantum. There are in the center, we have easy math problems that quantum computers could do or classical computers can do. And then we have this lighter blue, which is hard problems for classical computers. So there are some, as you can see within this circle, that are hard, just meaning that they take a lot of time to solve. And you can see the darker blue circle in this Venn diagram is where quantum can come in and help with these massively parallel quantum computations. But not every mathematical problem fits within the quantum possible. So yes, if you see down here, we have factoring. Factoring is what it's going to take to break an encryption key. And yes, we know that there is a quantum algorithm. There is a quantum algorithm that will do factoring really well. It just takes insanely large numbers of qubits in order to do it. So again, quantum isn't going to replace classical computing. It's just going to be another type of computer that has very specific purposes, like in medicine, where they're trying to fit a molecule, figure out how to manipulate a molecule so it can fit. Well, these qubits, they can pretty much map out like a protein sequence and say, put that into, if they had enough qubits, they could put this molecule in as qubits and say, what is going to make this fit? And the qubits will try through superpositioning, will try every possible permutation in seconds, and then the answer will come out. Here's how you would fit that. That's where quantum computing, that's the power of quantum computing. But as far as playing, are we going to see quantum powered Xboxes? I don't think so. I don't see the use case there, right? So hopefully that makes sense. All right, so I'm kind of being a little bit of a naysayer on it, but what is NIST doing about this? Well, NIST has been good. So NIST, so one of the things I should mention is, I meant to mention, is quantum there are types of encryptions that we currently don't believe that a quantum computer can crack. So going back here, we can find encryption algorithms that hang out in this part of the circle that quantum is not going to be able to solve. It won't involve factoring because we know quantum is really powerful at that, but we can do other encryption algorithms that quantum isn't going to help with. And so this is where NIST is now. NIST recognized this, and they've been starting around 2016. They started saying, we want to see some examples of quantum resistant cryptography, or as it's called in the industry, rather bizarrely named, in my opinion, post-quantum cryptography, or PQC, right? So this is the PQC timeline, and this was snapped from a presentation that was late in 2020. So we're here in the third round, and if you look at some of the candidates, these are different encryption algorithms that again sit over on that left side of the blue sphere that are believed to be quantum resistant. But I want to caution you, this is still very early. We're not even into the draft standards yet. Nobody has really been able to test that these are truly quantum resistant. We understand it's our understanding that they would be quantum resistant, but they may be there may be some really elegant standard classical computer algorithm that might easily crack one of these lattice-based or multivariate-based encryption algorithms. Yeah, a quantum computer can't do it, but maybe another computer can. So I want to caution you about thinking about jumping headfirst into these PQC algorithms. It's still early days. Moving on. All right. So with all that said, what are the next steps for a savvy security professional? So my advice is don't get caught up in the FUD and the fear, uncertainty, and doubt. We still have plenty of runway before quantum becomes a serious threat to our current approach. So if you've got data, though, that you need to encrypt and keep protected, keep it secret, it's going to be out there on the internet in an encrypted fashion or on a media that you need to keep protected for 20 years or more, well, you might want to start thinking about PQC algorithms. But remember, I said I don't trust these PQC algorithms yet. They're not fully formed. So my recommendation would be, if you have something you've got to put out there and you're worried about this 20-year shelf life on this encryption, consider using RSA and then layering on a PQC algorithm. So essentially double encrypting, which hopefully will protect you against a future state of quantum if we ever can get past some of these Moore's laws-ish barriers that just seem to make quantum so difficult to actually build out. But then you're not investing whole heart into PQC. You're not dropping the current RSA in favor of PQC, and then finding out that the method you chose has an easily exploitable backdoor, or not backdoor, but a weakness in the encryption. Too soon. All right. So here's my advice to everybody. Even if you don't have data that needs to be encrypted for 20 years, everyone should start beginning a path towards crypto agility. And what I mean by that is you need to start looking at where the various encryption algorithms exist in your organization. Where is RSA being deployed? Where does the RSA encryption algorithm exist? What's doing that? And then figure out if there's any way that you can change that algorithm or change the key length. Start understanding where your encryption algorithms lie and what your options are to either change the algorithm from RSA to something else or to change the key lengths. And if you find that things are hard-coded, like so many vendors will put things onto firmware and don't give you an option, start working with the vendors and start pushing on them to say, hey, I want to have the ability to select my encryption algorithm. You know, this is how, if for those who have been in security long enough, you might recall DES or triple DES and SHA-1. It took us forever to get rid of these weak encryption algorithms. They had been cracked, but yet they still were employed because so many devices or so many software products had the encryption algorithm baked in where you couldn't make any change. Well, we need to prepare to become quantum agile so we can move back and forth between whatever algorithm will keep our data protected. All right. God, are people still awake? I hope. All right, that's my quantum presentation on encryption. I'm open for any questions, quibbles, qualms, and clarifications that I can do for this.
Well, Rob, you do have a couple of questions.
Okay, how do I see those? Let me click on chat. I think
Yep.
Apologize. I didn't have chat open, so if I missed someone's question in the presentation.
Well, I can throw them out at you if you'd like, or
sure.
and of course, if somebody just wants to just chime in, feel free.
Yeah.
But we have so
it's an informal group. We're fam, right?
Right. So we were talking about the quantum computing and the fact it would take 20 million qubits. Thank you.
Uh-huh.
How long would it take with the current quantum computers to crack that RSA encryption, do you think? You may not know, which is fine, but.
Yeah, so this is what's weird about quantum computers. They don't, the way they work, the number of if they don't have sufficient qubits, they can't do it. There's no amount of running the algorithm over and over again. It simply doesn't work. as a matter of fact, if you know about, and I'll try not to get too deep into the weeds, it's all about factoring for primes, right? Or factoring numbers to try to look for prime numbers. The largest, this might be slightly dated, but it's not far off. The largest number that the current quantum computers can factor is, I think it's 21. It's the number 21. Like 3, 7, 1. Like we can factor these numbers in our head, and a quantum computer can't. It needs many more qubits in order to try every possible permutation and give you those prime numbers. Again, thinking about how to crack RSA through that brute forcing. So they simply can't, they're simply incapable at this time to be able to do it. Quantum computers can't, no amount of time will solve it with the number of qubits we have now.
Interesting.
Yeah.
So for the IBM system in the photo, was that magnetic? Do you know?
It is not magnetic. It is super cooled radio waves or microwaves. I want to say something like that. So they're using radio waves, and it goes through this. It's a beautiful machine. If you want to Google it, IBM just really, I mean, it's like a piece of artwork. It looks like a chandelier almost. And then it's immersed in this liquid helium that's keeping it's one of the coldest places in the entire universe, right? It's ultra cold here, like near absolute zero or down in that area. And that's how they're able to control the state of these radio waves and deal with this quantum entanglement that occurs, and the superpositioning of emulating the concepts of these superpositioning.
Cool.
But Google, I think, does it with lasers. I think theirs uses lasers, I believe. So they use light.
So another question, curious what your opinion of blockchain versus quantum versus encryption we will be seeing in the next 10 years.
Yeah, so interesting. That's a lot of people are wondering right now, blockchain uses very similar encryption to what we're talking about with RSA. Many of these are using a strong encryption algorithm that eventually quantum will be able to crack if we can scale it up into the millions of qubits. So that's where blockchain is vulnerable unless that, well, so what needs to happen is the blockchain algorithm needs to change to be a post-quantum cryptography. So they need to change the algorithm to incorporate post-quantum cryptography. And again, if it were me designing it, I would say layer in an existing protocol that we trust and then put a PQC algorithm on top of it. So you're doing a double encryption, but so you're theoretically quantum resistant, but also classical computer resistant. And then let me see, quantum, blockchain. Yeah, so Bitcoin, right? A lot of people who are worried about Bitcoin. One of the things that makes Bitcoin so compelling is that the code doesn't change. There's only so many Bitcoins that will ever be minted, and the algorithm is held strong all these years. This could, in theory, break that. But again, I think we're a ways away.
That's all the questions that are in the chat. Does anybody else have any questions? I mean, feel free. Anybody?
Hey, Rob, do you need a fusion reactor to power one of these things when you get to 20 million qubits? Or
Right, we don't know, because no one can realistically, with the approaches that are being done now to build these quantum computers, it's unimaginable what it would take. It would be miles and miles of one machine, and these properties that we're talking about, this superpositioning and entanglement, they're the current state of quantum mechanics. And this stuff is, I tell you, it's very bizarre how some of these entanglements work, where two qubits that are entangled can be separated by, in theory, miles, and yet you change one qubit and the other one changes at the same time. But I still think that we just don't have, we haven't found the way to build Just like we haven't found a way to build a practical a fusion reactor, we haven't found a way to build a practical quantum computer that can, at the scale needed to do what we're talking about here, cracking these algorithms. Did I bore you all to death? Was this at all interesting? I'm also curious, I should have put a poll. Did my description of quantum computing help make it, at least try to understand the difference between quantum without making it too challenging or too into the weeds, but yet it trying to contrast what a quantum computer can do or how a quantum computer works compared to a classical computer. Hopefully that some of those concepts stuck.
Hey, thanks.
Well-
Appreciate you doing that, because as just dumb sales guy, I was like pretty impressed, and I found it very interesting. So, kind of blew my mind. Maybe a little late in the day for that, but no, I appreciate it. I never really, I see it in the news and
Right.
stuff about quantum computing, but I just never delved into it. So I appreciate it. It was pretty cool.
And now you know about the qubit. You can speak like a guru.
Yeah.
The superposition and all that good stuff. So, and
Yeah,
quantum-
actually, the chat is coming through in a lot of positive comments on the chat. So I think it was definitely a good talk for real.
I hope everyone enjoyed it. Thank you.
Yeah, absolutely. If I could get you to hit the stop record button.
Yep.
But if anybody else has any questions at all,